All right, friends, 3 o'clock. Welcome back to your favorite class. Yes. Nice day out there today. Would like to be out there. Very nice. Okay. Announcements for the class. First, your simulation number 3, due on Friday. A lot of people already got it done. Turning it into me, emailing it to me. Beautiful. Beautiful things. So keep it going. You got all the tools in your tool bag ready to do it. Just takes a little bit of time. It's a little tedious. Do the algebra and do the computation, but it should be pretty straightforward. So do that. Get it in. All right. Announcement number 2 is homework number 6, which is the last homework for the class, which will be on gears, which you're talking about right now. Will be due next Tuesday. So I posted that. Do 1 week from today. You should be able to get through it, even a majority of it by the end of today, and almost all of it by the end of today. Definitely by the end of tomorrow, you should be able to get it done. All right. Then your exam number 3 for the class, which is kind of like a final, but it's not really a final because it's not cumulative. So I'm calling it exam number 3, is going to be 1 week from Thursday. So next week, Thursday. My plan for the class is like this week will be really like the last week that we talk about new stuff. All right. So my plan this week is kind of finish up gears, do a couple example problems, and chill. Next week, chill. Like probably not gonna have any lecture formally. It's gonna maybe be like one review day on Wednesday where we do some practice problems. But Tuesday, probably not even gonna have lecture. Just give you guys a break because I know you all got finals going on next week. So I'm just chilling next week. All right. I don't have anything planned for next week really, except the test, which is on Thursday. So that's what's happening for the class. All right. Cool. Cool. How do we like the meme today? When you're in the middle of an exam and the professor is explaining something to someone, you guys do the thing where you like cup your ear and you're like trying to listen real close. Like, what's he saying? Is he giving out answers over there? Yeah. It's maybe a little close to home right now because we all like got headphones on. So yeah, maybe that's happening. Yeah. All right. So there you go. Anyways, onward. Lecture. A little bit of a slog today. So we just got to get through some math and talk about some very basic things relating velocities of gears, but a little bit of a slog today. We'll do some example problems tomorrow that'll help sort of solidify the stuff that we talk about today. All right, so here we got lecture for 512, and let's dive in. And remember that we're talking about gearing systems. All right. Our most basic gearing system consists of 2 gears that are kind of pinned at the center. So this was our most basic gearing system. And remember, we had one gear that was kind of the gear that's driving everything, and we called this the pinion gear, or simply just the pinion generally. And that guy is being driven by some motor, or he's in charge of setting the tone for this whole system. We had a little bit of vocabulary associated with these gears, and the major one I want you to take away is that there's this circle that exists that kind of like cuts through the middle of all the teeth on this particular gear here that I'm sort of like trying to draw on this drive gear, but also exists on the driven gear, which we call the pitch circle. All right. This has a diameter, which we call the pitch diameter, which has the variable associated with it, which is little d. All right. Now, this pitch circle has the diameter associated, which is this little d. So I can sort of draw that in here if it sort of helps. And so here's this pitch diameter, little d. And we'll say the number of teeth on outside we denote with the letter N. Okay, so you might see it as Ni, where I is the gear in the train that you're talking about. So N1 would be like the number of teeth for gear number 1, N2 would be like the number of teeth on gear number 2, and so on and so forth. Okay, then the big vocabulary word that kind of came from this was the ratio of the number of teeth to the pitch diameter, which we called the diametral pitch. And here we gave that capital P, which is the number of teeth divided by the pitch diameter of that particular object. All right, this is number of teeth divided by pitch diameter. And we said that if 2 gears are mating with each other or meshing with each other, They must have the same diametral pitch. Okay, so those are the big takeaways that we had from Friday's lecture. All right. We also discussed some other general vocabulary about gears that are useful for you to have as engineers when you're going into conversations about, potentially making a gearing system. When someone says to you, like, what's the gear ratio, which we'll talk about today, or what's the addendum, what's the pitch point, what's the pitch circle, yada, yada, yada. You can actually understand what those general things are. So we had some vocabulary that was associated more or less with the teeth of the gear that looked something like this. All right, so our vocabulary in terms of like a picture looked something like this. And so I was just talking about the pitch circle, which is like the circle around the gear upon which all these calculations are based. All right, so the diameter of this guy would be the little d that I just talked about. So there's your pitch circle. We also talked about addendum and dedendum, which is the distance from what is the mesh point to like the top or the bottom of the tooth. All right. And we also talked about circular pitch, which is the distance between the same point on two teeth in the series. All right. So these are just some words that you should sort of have in your mind at the ready for general conversation about gears. All right, so we did some nomenclature. We talked about a couple of different gearing types: spur gears, pinion gears, bevel gears, worm gears. We talked about all those sorts of things. All right, so that's just a reminder of what we did on Friday. What I want to do now is just a little bit more nomenclature, and then we'll get into kind of the math behind how the torques and the velocities are transferred between a series of gears. All right, so new material here now is just some quick more vocabulary. And this has to do with two gears that are in contact with each other. All right. You will talk more about an image that looks like this when you get to ME2003. But again, we see things that we've already sort of talked about, being like the pinion gear, or the one that's sort of driving the system, and also the driven gear. So that is, sort of his speed and his motion is being dictated by how fast the first one is being pushed. All right. So things that we already kind of know: addendum circle, pitch circle, dedendum circle. These are all things that we talked about last time. Pitch circle and addendum circle. You sort of see all of them with this particular image. So this is two gears that are in mate, and we're sort of modeling the gears by these circles that are of interest and of importance during the mating process. All right. Here is your meshing point right here. And you'll see a couple of other words that pop up in this particular mating image. Things like the pressure line, angle of approach, angle of recess, so on and so forth. Those sorts of things and those sorts of terms are associated with like the stresses that form between the teeths of the gears as you're sort of moving them. And that's not something that we're going to talk about in this class. So generally, discussions about stress relationships inside gears, all sorts of things, those are going to be reserved for your ME363 class after you've gone through 2004 and 3005. Okay, so stresses exist at interfaces of teeth, but that will be discussed in ME363 after you've taken 2004 and 3005. By the way, I'm teaching 3005 in the fall, so if you're enjoying my style, take 3005 with me. Rawr. All right. That's Mechanics of Materials 2. So if you haven't taken Mechanics of Materials 2 yet and you need to take it in the fall, sign up for my class. I think it might be full, but I'm trying to get like more spots open. So keep checking back. All right. And if you don't like me, take it with somebody else. Fine. Rawr. All right. So the point is there are some additional vocabulary you might see with gears in the future, but what we care about in this class is velocity analysis, okay? But in this class, we focus on velocity analysis of gears in a train. All right, choo-choo, homies. We're talking about velocity analysis of gears in a train in this class. Again, this class we care about position, velocity, acceleration. Not even really going to talk about acceleration. We're going to mostly talk about velocity, which is kind of the important bit. All right, so some additional vocabulary, and you will talk more about stresses at the interfaces of various gears when you get to 363, but in this class, we care about velocity. So, if that's what we care about, let's freaking talk about it. All right. And we'll consider first the most simplistic situation, which is just two gears in a mesh. Right? So the picture you should have in your mind is, here's gear number 1, and it's pinned at the center there, and it's meshing with gear number 2, which is going to look something like this. Not necessarily the same size. In fact, we're going to talk about gears with different size to build general relationships. All right, and they're going to mesh right here at this particular point. And we'll call this point A. All right. So here's gear number 1. And here's gear number 2. And let's say that each one of these gears has an associated radius of the pitch diameter. So what we're looking at here, these are the pitch diameters. And so this has a radius associated with it that we're going to use for our calculations of R1. This guy has a radius here of, you guessed it, R2. And we'll have a diameter of D2, so you could say that guy has R2, D2. All right. And there will be some associated angular velocities with these two particular guys. All right. So let's say this guy has some angular velocity here, which is omega 1. And to mate properly, this guy is going to have an angular velocity in this direction, which is omega 2. All right. So we'll assume that gear number 1 here is the driving gear. So gear 1 is pinion. Meaning that it's forcing the system to go, right? So if this is the particular case, we know from our angular velocity and position equations that there is a linear velocity that exists on that particular gear that is something like omega cross r. So linear velocity at A is VA equals omega cross r. All right, we know this from like months ago. God, it's so long ago. But I told you, it ain't going away. Rawr. All right, so omega cross r. Magnitude, since this is pinned at the center, will obviously be the magnitude of the velocity of A is going to be equal to omega 1 times R1. All right, V is omega R. We saw this countless times in this class. Well, I bet it is not countless, but probably 50 times in this class we've seen this. All right, velocity at point A is omega 1 times R1. Also, we know that these two rigid bodies are in contact with each other. And if they're in contact with each other without slip, which is what we're assuming, then the velocity at the point of contact of these two different rigid bodies must be the same. So VA shared between gears 1 and 2. So therefore, we also have the magnitude of VA is also omega 2 times R2. right? Since it's shared at this particular meshing point where they're touching each other, we have that particular state. Okay, so therefore, the relationship emerges here, which is something like R1 omega 1 equals R2 omega 2. All right. So the radius of the first times the angular velocity of the first is the radius of the second times the angular velocity of the second. All right. That is a useful relationship to know. And it all comes from the idea that they're not slipping against each other and the velocity is the same at the point wherever they're touching each other. Okay, so we can rewrite. Usually when you're talking about gears, you're talking about the ratio of the velocity of the gears. So if you ever hear something like the gear ratio, you're talking about what is the angular velocity of the output gear given some information about the input gear. So you're talking about this ratio. So we're going to rewrite as a ratio of angular velocities. That's going to be that omega 2, the output angular velocity, normalized by the input angular velocity, this velocity ratio, is equal to R1 over R2. Or if we're talking about pitch diameters, you could have D1 on D2. All right, where this is the pitch diameter. This here, the ratio of the output angular velocity to the input angular velocity, is known as the velocity ratio. So we give that the symbol MV. So here's the first kind of takeaway equation from this portion of the class when we're talking about the ratios of the angular velocities of the gears given their various radii. Okay, so here is angular velocities of gears. So here's the pitch radius. This is the pitch diameter. And here is the velocity ratio. All right. So this is going to be the first and most basic relationship that we have between two gears that are in mesh with each other, is that this velocity ratio of output angular velocity to input angular velocity is a ratio of the radii of the two individual gears. Right? One last thing that we'll say is that we can bring in number of teeth into this by introducing diametral pitch. Let's recall. Diametral pitch, which is that the diametral pitch is equal to the number of teeth on that gear divided by the pitch diameter. All right. Rearranged is diameter is number of teeth on diametral pitch. All right. So if we want something like D1 is N1 on P and D2 is N2 on P, we know that if they're in contact with each other, the P must be the same. All right. So we can, let's say, plug D1 into here and plug D2 into here, and we can come up with this expression, not in terms of the pitch diameters or the pitch radii, which may be a little bit difficult to measure directly, but we can do it in terms of the number of teeth, which is not difficult to measure directly. Right? So in terms of number of teeth on gears, we have the following, that the velocity ratio here is this output angular velocity omega 2 divided by the input angular velocity omega 1, which is the diameter of the first divided by the diameter of the second, which in terms of number of teeth is a direct relationship, N1 on N2. So here you go. It's sort of your big takeaway. Velocity ratio relating output angular velocity to input angular velocity and number of teeth on each particular gear. How are we doing out there? We all awake? If not, wake up. Time for you to put on a little makeup. That song might be a little too old for you guys. Yikes, Chop Suey? God, what year did that come out? Like 2000? Maybe earlier than that. It's like late 90s. Oof. You guys may have not even been born when that song came out. Wake up! Time for you to put on a little makeup. Something, something, shake up. Rawr. All right. Go look that up. I don't even know. Chop Suey. When did that come out? Long time ago. This equation here, back to reality, is the basis for what is called the fundamental law of gearing. All right. The fundamental law of gearing, it has two parts to it. We only really care about part number one to the fundamental law of gearing because that's all that really is important to us. It tells us about the ratio of the velocities inside of a gear train. That's what we care about, velocity analysis. There's also a second part to the fundamental law of gearing, which has to do with stress analysis and pressure lines, which not as important for us. You'll talk about it in 363, but I was asked to introduce it to you in this particular class. So in 2003, we're asked to introduce the full fundamental law of gearing, and so I will give you both parts, though I will tell you we are not going to touch with a 10-foot pole the second part of this particular fundamental law of gearing. So let's do that. All right, two parts. Rawr. Part number one is related to the equation that we just wrote down. All right, and that is the angular velocity ratio of all gears in a meshed system is constant. All right, so we see that with this equation. All right, so I'll give you a sec to write that. The angular velocity ratio of all gears in a mesh system is constant. All right, so we sort of see hints of that here. All right, here's the ratio of the angular velocities. It equals a number. Right? When we build on and we put additional gears on the train, we will see that this value maintains its consistent number through the entire chain. All right? This is the part we care about. The second part, which we don't care about right now, is the second tenet of the fundamental law of gearing, which is not going to make any sense to you, but I need to introduce it or talk about it anyways, so that when you go to ME2003 and they ask you, have you seen the fundamental law of gearing? And you can all say yes, but we don't really know it very well because we skipped over part number two. That's what you're going to say. Raise your hand and say that exact and say that's what Dr. Hard told us to say. All right, here, the common normal at the point of contact must pass through the pitch point. Yeah, that's not going to mean anything to you right now. Promise. Not ask you about this. If you open up any mechanical engineering handbook and you go to the fundamental law of gearing, you will see these two tenets. We are not going to talk about number two. You will talk about it in ME363. It more or less relates to this picture here, where you're talking about the pressure line being normal to the point of contact and passing through the pitch point. That's kind of what it's relating to, and it has to do a lot with stress calculations, but we don't do stress calculations in this class, so we don't care about that. All right. Back off. Damn. All we care about is number one. And remember, number one is really digging in on the equation that we sort of like wrote up here, which is this velocity ratio between any two gears in the system is constant, some number. It's a constant value. All right, so let's expand upon that idea, and let's talk about bringing in more gears into our system by looking at gear train analysis. So we've talked about the most simplistic gear train that there is, and that is between two different gears. Now, what happens if we bring more gears into the train? We're going to start to create what are known as simple gear trains. So let's look at those. Choo-choo. It's time for a simple gear train. Yeah, choo-choo. Here we go. Simple gear train. Bam. All right. There's your simple gear train. Here is the gear number. All right, so in this particular train, we have 5 gears, which are labeled numbers 2 through 6. What the hell? Okay, by convention, usually the first gear in a train is labeled as gear number 2. That's because the motor inside the engine that drives gear number 2 is gear number 1. Okay, that's that. So usually in a gear train, you'll start to see that first guy as gear number 2. That's your gear number. On the right-hand side, you see all these things over here, which are the number of teeth on each particular gear. So N2 is the number of teeth on gear number 2, N3 is the number of teeth on gear number 3, so on and so on and so on. All right, so that's the basis for this particular figure. Other things that you'll notice in this particular figure is that all of these gears are pinned about the center, and they only mesh with up to 2 additional gears. Right, so that's an interesting thing to note. And here we'll see that we have an input angular velocity, omega in. So this is the driving gear or the pinion gear. And then this guy here, this is your output angular velocity on the back end. You'll notice that they're in the same general direction in this particular image. This image, they're utilizing the color gray to show you which gears are in sort of the positive angular velocity, and the color red to show you which gears would be going in the negative angular velocity. All right, so again, if this guy has the positive general direction, then this guy must oppose it in this general direction here, so it's going to be a negative angular velocity. All right, so that's what's going on in this picture. So let's get rid of all this nonsense and let's write some stuff down on the page. All right, gear trains. Are collections of 2 or more gears in mesh. All right, we've talked about that already. Choo-choo, away we go on our gear trains. All right, a simple gear train is one where every shaft has only 1 gear attached to it. Okay, so in this particular example, there's a shaft here upon which this gear spins. There's 1 shaft here upon which this gear spins. 1 shaft here, 1 shaft here, 1 shaft here about which this gear spins. That is not the way that your car clutch works, okay? Your car clutch has multiple gears on the same shaft. And when you switch gears, you switch which gears are in mesh with each other. That's the way that your car transmission works, all right? Your car transmission, not a simple gear train. It's a very complicated gear train. It's called a compound gear train, all right? We'll talk about those in just a second. This is a very simple train, 1 shaft per gear. And it's a good basis for conversation for us to start our analysis, even though systems like this are hardly ever seen in practice. All right. We know from fundamental law of gearing, velocity ratio must be constant. So what I mean by that is the velocity ratio, which tells us what the angular velocity is at the output given the input, so something like omega 6 over omega 2, is going to be a constant, which is the combination of the products of the individual meshes along the way. All right, so this is going to be equal to, we know that gear number 2 has to mesh with gear number 3. Gear number 3 has to mesh with gear number 4, so on and so forth. So it's going to be here something like omega 3 on omega 2 times omega 4 on omega 3 because of the mesh between 3 and 4 times omega 5 on omega 4, which is the mesh between 4 and 5, times what is omega 6 on omega 5. All right, because they're all sort of meshing with each other along the way, we're sort of keeping this consistent along the way as we go. All right, so you'll see that because of all these meshes that we have relating 1 to 2, 2 to 3, 3 to 4, 4 to 5, so on and so forth, that in the end, we cross off all the guys where we have redundancy, and you're left with omega 2 on omega 6, which is the velocity ratio of this particular train at the output given the input information. All right? So that's what we have for this particular system. All right? We could write this in terms of numbers of teeth. Since we know generally that something like omega 3 over omega 2 is N2 over N3, we can extend that general idea to the equation above and say that like the velocity ratio is equal to omega 6 on omega 2. But now we have this relationship which is inverted, which is something like N2 on N6, which is here N2 on N3 times N3 on N4, the mesh between 3 and 4, multiplied by the mesh between 4 and 5, multiplied by the mesh between 5 and 6. Right. This is your general idea here, giving you this velocity ratio. We just sort of like showing how to get output velocities given a chain of these, what you might consider each one of these individual points meshing with each other as like a 2-gear train. So 2-gear train here, 2-gear train here, 2-gear train here, just pushing it all the way down the line to show what the relationship is between the input and output of the entire train. So more generally, we can see that the ratio between the angular velocities of any two pieces and the number of teeth on those two particular gears is a consistent value. So we'll say that in general, and this is the equation you really want to go with, is that the angular velocity of gear J over the angular velocity of gear I, so we'll say in general, or 2 gears in a train, that particular ratio, omega j over omega I, is going to be the same as Ni over Nj, which is the same as Di over Dj. This comes back to what we saw basically just for 2 different gears, right? So 2 gears in a mesh has the same general relationship. We're just making it now more specific for any 2 gears that are in a train with each other. All right. There's a slight mistake here in the notes, and I'm going to correct it on the fly. All right. We know that if we go to this train and we look at the direction of the input angular velocity and compare it to the direction of the output angular velocity, if we have an odd number of gears in our train, they will be the same direction. We have an even number of gears in our train, they will be in opposite directions. Okay? So to distill that down, if j minus I is an even number, then angular velocities will be in opposite directions. All right, the notes does not say this correctly. Okay, I'm gonna have to update the notes. If I minus j, sorry, j minus I is an odd number, okay, meaning you have an odd number of gears in your train, angular velocities will be in same direction. All right. So there you go. If you're looking at 2 different gears, and you know, let's say gear 5 in the train and gear 2 in the train, and you know the number of teeth between the two, you can determine what the angular velocities are going to be between the two, or at least the ratio of the angular velocities between those two. All right, that's our general concept or general idea. Okay. That's the takeaway there for simple trains. Now, simple trains are not very useful in practice because how often are you going to have a situation where you have a bunch of shafts that are in line with each other that need to like somehow be driven perfectly at these ratios where you'd have these simple gears that make it happen? Okay, it's just like impossibly rare in practice. All right, so I'll say that simple trains are very rare in practice. Except for like two gears in a train. Obviously, like a two-gear train is very common. All right, but anything more than two gears in a train is like very rare to see in practice. Okay, more common are compound gear trains and reverted gear trains. All right, and these are what we're going to talk about next. So compound gear trains will have more than one gear per shaft, and reverted gear trains will be configured in such a way that shaft directionality is maintained. So we're going to get to that in just a little bit. But first, let's talk about compound gear trains. So these guys first. All right. Much more common to see a compound gear train or a compound reverted gear train, which we'll talk about in a little bit. But a compound gear train looks something like this. More than one gear per shaft. So at least one shaft with multiple gears. So it will look like this bad boy. Rawr. Multiple gears, same shafts. Rawr. All right. So here we see multiple gears. We're looking at this from above. Multiple gears on the same shaft. All right. So this is a compound gear train. And there's some kind of funky things that happen here, or we'll go on with the analysis, but we'll power through those as we sort of see them. Okay. So here's your input shaft. Again, this is like your pinion for the system. And then here's like your output shaft when this guy is being driven, more or less. And so what I want to know is if I know all the teeth on each one of the gears, and I know what the input angular velocity is, what is the output angular velocity? That's all we care about in this class. Velocities, right? All right. So at least one shaft with multiple gears. And let's kind of go through and step through our analysis of this particular guy. Hey, page down. Let's go. Arr. Stupid technology. All right. Obviously, the gears that are on the same shaft will have the same angular velocity. We just know this for rigid bodies. All right. So what I mean by that is because this gear and this gear are rigidly attached to the same shaft, whatever angular velocity this guy has is going to be the angular velocity of gear number 3, which is going to be the angular velocity of gear number 4. They're all rigidly attached. They all have the same angular velocity. This goes back to week number 2. Where the heck you been? Right? So gears on the same shaft will have the same angular velocity. So let's step through what the velocity is of 2 relative to 3, then 3 relative to 4, then 4 relative to 5. All right, we'll just step through our analysis, okay? So that we can figure out what the output angular velocity omega is given the input angular velocity. So if we have omega 2 and n2 through n5, what is omega 5? Question. What is omega 5? Well, let's look at this. So from 2 to 3, we have our very simple relationship from 2 to 3. It's just a simple mesh here between 2 and 3. And so we have the relationship that, like, the output omega 3 on the input omega 2 is the ratio of the teeth on these two guys, N2 to N3. This is what we talked about at the beginning of lecture. So we could write here that the angular velocity of gear number 3 in this train is the ratio of the teeth of the two times the input angular velocity omega 2. All right, so we'll keep this guy and we'll come back to that. That is your angular velocity of sort of the second gear in this train. All right. From 3 to 4, well, we just said that since they're on the same shaft, omega 3 and omega 4 are the same. So we could continue and write directly, omega 4 is still the same relationship, which is the number of teeth on the second divided by the number of teeth on the third, multiplied by the angular velocity omega 2. Okay, so here we'll label this double star. And finally, if we analyze what's going on between 4 and 5, again, we'll use like the same relationship that we have up here. Omega j on omega I is ni on nj. We have that omega 5 on omega 4 is n4 on n5, or that omega 5 is this ratio n4 on n5 times omega 4. And we'll plug in this double star. And you'll get that omega 5 here is n4 on n5 times n2 on n3 times omega 2. All right, so this is your final output angular velocity given the input angular velocity. Now, the reason why I write this out fully and why we go through the analysis of this kind of simple compound gear train is because we see like a pattern emerging here. All right, what is the pattern? All right. Like I said before, gear number 2 here is the pinion. This guy drives number 3. All right. So here is number 3. Number 3 is being driven. All right. Maybe I'll do that in red so that we can distinguish. All right. A very similar idea would exist for gears number 4 and 5 if we sort of assumed that 2 and 3 were not there. If 2 and 3 were gone, all right, so imagine putting your hand over numbers 2 and 3. Okay, so pretend that they're just not there for a second. If that were the case, then 4 would sort of be like the pinion. So I'm going to call this a pseudo pinion. Okay, because it is driving number 5. All right, so here the idea is 2 is driving 3, and if we just got rid of 2 and 3, then 4 would be driving 5. So we have this idea and this concept of like driving versus driven gears in this compound system. And what you'll notice is that in the numerator here, we have numbers 2 and 4, which are related to pinions, or the driving gears. And on the denominator here, we have, where's my red? Give me my red. Rawr. 5 and 3, which are like the driven gears. All right. So we rearrange here, and we could write omega 5 over omega 2, if we just took omega to the left-hand side. Remember, this is my velocity ratio of my system, 5 on 2. Here this is something like N4 times N2 over N3 times N5, where both of these guys are driven, and both of these guys are driving, or pinions. All right, so we can see this pattern emerging if you have a compound gear train. What we saw before is a two-stage compound gear train, where we have like this here is stage number 1. This here is stage number 2. Okay, so we have a two-stage compound gear train, right? The general idea holds, all right? So we would generally say in a compound gear train, that the velocity ratio is omega j on omega I is going to be equal to this velocity ratio mv, which is the product of teeth on driving gears divided by product of teeth on driven gears. All right, so there you go. There's your general relationship for a compound gear train. All right. We saw a two-stage compound gear train, but later on we'll show a three-stage compound gear train, which generally has the same idea. Okay, so this holds for all kinds of gear trains. So we saw a two-stage. This is a three-stage. Don't be scared. No being scared. Okay, so stage number 1, stage number 2, stage number 3. The same idea would still hold, is that you have driving gear, driving gear, driving gear, all driving, the driven gear, the driven gear, the driven gear. So you're going to have something like omega out over omega in will be equal to something like the product of the teeth on the driving gears, and 2, and 4, and 6 on the product of teeth of the driven gears, and 3, and 5, and 7. Same general principle will hold in this particular configuration. All right, you can add more and more and more stages in your compound gear train and just have the same general relationship: driving, 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 driven, 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 so on and so on and so on. All right, last comment that I want to make is in relationship to the gear ratio. Most of the time when we're talking about gearing systems, you'll hear the gear ratio, not the velocity ratio. They are not the same. The velocity ratio and the gear ratio, not the same thing. They are inverses. Right? So what I mean by that is that the velocity ratio, mv, which is usually something like the output over the input, is the inverse of the gear ratio. All right? Or the gear ratio is the ratio of the input divided by the output. Almost exclusively, when people are talking about gearing systems, they're talking about a gear ratio. And personally, thinking about a gear ratio to me is easier than thinking about a velocity ratio. So if I want to think about a gear ratio, I don't want to think about the ratio of what I put in versus what I put out. So if I have a gear ratio of 80 to 1, that means I put in 80 RPM and I get out 1 RPM. If I have a gear ratio of 1 to 80, I put in 1 RPM and I get out 80 RPM. All right. So usually when you see data sheets about like the gear ratio of the gears inside of some black box that you just bought, and you see something like 3,600 to 1, that means you're putting in 3,600 RPM and getting out 1 RPM. All right. So usually you'll see things in terms of the gear ratio, not the velocity ratio. So very important to keep these two different things straight, because the ratio of in to out or out to in is different, gear ratio and velocity ratio. Okay. All right. So that's it for today. Thanks for coming. We'll actually do an example problem with numbers tomorrow to sort of like lock this in and tighten it up. All right. So thanks for coming, and we'll see you tomorrow.